Welcome. In this lecture, we will discuss about homogenization and gas stirred ladle. Basically, the gas stirred ladle is used to homogenize the bath homogenize the bath. Okay, so there is a homogenization and gas stirred ladle. Now, here basically we will discuss the significance of homogenization in ladle, why it is required, and then we will discuss about the mixing time and correlation. And mixing time is basically used to characterize the extent of mixing in a bath. Okay, and mixing time and this correlation we will discuss, and also we will discuss the effect of nozzle configuration, different types of nozzle configuration for gas stirring in the bath. So these are the concepts that will be covered. Now here, first of all, the significance of homogenization in the ladle. Why homogenization in the ladle is important? Homogenization means basically thermal homogenization as well as compositional homogenization. Now, what is that? Basically, the stratification of temperature in ladle is a usual phenomenon. What happens is that after you tap the liquid steel in the ladle, then you take the ladle from the SMS to the caster, and in this process you do a lot of secondary processing also. And during this time, that is, the liquid steel loses its heat, okay, through its walls as well as through the open face to the atmosphere by radiation mostly, and through the walls also it loses a lot of heat. And as a result, the thermal stratification takes place in the bath, in the liquid bath. And the stratification, if you want to see, it will look like this. If you have a ladle like this, sorry, 1 minute. If you have a ladle like this, you have a ladle like this, and then this is the ladle, say, and so this is here. So you can have this type of stratification of temperature because heat is losing, right? Heat is losing from the wall like this, and this is heat is losing everywhere, and then from the top surface also you may have some slag layer also. Okay, from here there is the heat will be losing. As a result, you will have this type of isotherm. This is T1, say, this is T2, this is T3, and obviously T1 greater than T2 greater than T3. So in the ladle, this type of stratification take place because heat is losing from the side wall, all four walls. As a result, all three walls as well as from the top surface, it is losing. So you will have this type of contour, a circular contour somewhat like that, and the outer contour will have the minimum temperature, and as you proceed towards the center of the bath, the contour will have higher temperature. So this type of stratification take place. So, and we need to get rid of this thing. Okay. So stratification of temperature in the ladle is a usual phenomenon. It happens. Also, the compositional homogenization is also an issue to avoid compositional stratification in liquid bath. Compositional homogenization means if you make some addition, alloy addition on anything, and in that case, it has to be mixed within the bath for an uniform composition. If you don't mix it properly, there can be a compositional stratification also. Okay. So thermal stratification, compositional stratification, those are the things, and that will be take place in the ladle. And for the concast, that is, if you want to for the continuous casting, right? Continuous casting, the liquid with the fixed superheat can only be cast. That is, if you change the superheat, liquid superheat, if you change, that is when you are pouring the liquid from Tandis to a mold, then when you are pouring the liquid into the continuous cast mold, it should have a fixed superheat, because that is the way the heat extraction from the mold, secondary cooling zone, from here, heat extraction from the continuous cast mold is fixed that way. This is the rate at which we will extract the heat such that you can develop a certain amount of skin thickness such that the material come down smoothly, because continuous casting, it is a continuous process. Okay, so the speed of the casting and the superheat, everything should be constant, and this will be commensurate with the amount of heat extraction through the wall, and then only you can cast it properly. Otherwise, there will be failure in the casting. You cannot cast it properly with a lot of defects, and all these things will be there. So continuous casting requires a fixed superheat. So any stratified liquid, that is the temperature, liquid with the temperature stratification, cannot you put into the mold. For example, if you use the trimming ladle and you have a temperature stratification, then what will happen? Initially some low temperature fluid will come, and then slowly from the core you will have high temperature liquid will come. So the superheat will increase with time, and that is not acceptable. That can happen. So that is the thing. So you should have a fixed superheat, and no stratification will be allowed in the ladle. Similarly, the compositional stratification, if you have certain more composition of the liquid and then less composition, as a result, during solidification also, you can have a macro segregation. You can have macro segregation. Macro segregation is a defect, because in some location you can have impurity or the alloying element, whatever it may be, it will be segregated, right? So some portion, some place it will be more, some place it will be less. That will give rise to a stratification. Compositional stratification in the ladle can give the your macro segregation into the bath also in the solidified cast. And macro segregation is a defect, right? I will talk about that. And now, so all these things can take place. So basically what we want to do, we want to eliminate the thermal stratification, we want to eliminate the compositional stratification, and that we do in the ladle by using gas stirring. It is more popular. Stirring mechanism is the gas stirring from the bottom. Gas stirring from the bottom is the most stirring mechanism, because the mechanical stirring is not a very good idea in the ladle, and this is the gas stirring which has got the prominence in the ladle. Okay, so inert gas stirring and the homogenization, I will talk about that. So it is basically this gas stirring is used to eliminate both the thermal and compositional stratification in ladle and improve the kinetics of the reaction. And what happens is that when you inject the bubbles from the bottom, after some time you get a steady state bubble plume. What is called a plume is there, and then with a dynamic size range of the spherical cap bubble finally forms. Basically what happens, from here you generate the bubbles, and the bubbles moves up, and obviously when they are moving up there is a continuous breakup and coalescence of the bubble, and finally they come to a dynamic equilibrium kind of thing, that is the bubble size, shape, distribution become constant, and this is called the bubble plume. And bubble plume come to a steady state after some time, that is, it comes to a steady state with a certain distribution and size of spherical cap bubble as a function of axial distance. Obviously as you move up, the spherical cap bubble will have bigger size. Here it is little lesser. As you are in the more deep, you will have less size. So size, shape, distribution, everything become fixed after some time. That is called the steady state bubble plume, a form finally forms, and the buoyancy, basically the bubble plume moves up, and that basically transfer the energy. As the bubble moves up, it increases in the sizes and then transfer the momentum to the liquid. Okay, so buoyancy in the bubble plume sets the liquid melt into recirculatory flow. This type of recirculatory flow pattern is set up into the bath. Okay, so it is basically the buoyancy of the bubbles that basically transfer the energy. This buoyancy is the source of energy, or the potential energy. That is the source of energy by which the liquid is set into a recirculatory motion like this. And also you can find at the top, these bubbles finally escape through it breaks the slag layer and escape to the atmosphere. And also liquid are moving in a radially outward direction. So it basically, in this region, the slag is taken away. So when the bubble is pushing and the slag is taken away, and then in this region, what happens is that slag get opened up. Okay, so what happens here, that is the slag get, in this case the slag get exposed, that is the slag layer get broken, and the liquid metal get exposed to the atmosphere, and this region is called the slag eye. Okay, this is not a very good thing, because through slag eye, liquid metal can have a direct interaction with the atmosphere. So nitrogen can get into it, oxygen can get into the liquid metal, and that can produce a lot of inclusion and all these things. So slag eye is not a good idea. So thing is that always the attempt is made such that we can reduce the slag I. And obviously the slag I increases with increase in the gas flow rate. More the gas flow rate, bigger will be the slag I. So you have to judiciously use or the gas flow rate from the bottom. Obviously, higher gas flow rate which intensely stirs the bath, and some cases it is required, like if you are doing a desulfurization using synthetic slag, you require a very high stirring in the bath such that you can emulsify the slag into the liquid melt, and that increases the kinetics of the process. So in that case, you require a very high bath stirring, right? Again, but in case of the homogenization of the temperature and composition, then you don't require too much of stirring. A mild stirring is sufficient. And in case of the mild stirring, your eye opening is also less. That is a good, because you don't have much of interaction. So that is the thing. So in that case, very judicial, that is the gas flow rate judicially controlled. You have to minimize the slag I. And for desulfurization, we use basically high gas flow rate, that is of the order of 1 normal meter cube per hour per ton. Okay. And in case of the thermal homogenization, thermal or compositional homogenization, a 0.1 normal meter cube per hour per ton is sufficient. Okay. So that is the way the gas flow rate is controlled to control the I. And based on the steady state energy balance, right, you can calculate, if you can do that, people has done it, based on steady state energy balance, you can calculate the velocity of this plume, that is the velocity of the bubble plume. You can calculate, that is the velocity at which the bubble plume moves up, as well as you can calculate the velocity of the circulatory flow. Okay, so both the things you can do. So, and how you can do that? That is, you make an energy balance, and then you can establish some empirical correlation. Okay, so you can find, that is the plume velocity can be given by this thing, that is the as a function of gas flow rate of the gas flow rate, and then there is the length of the vessel, as well as, or the height of the vessel, as well as the radius of the vessel. As a function of design parameter L and R, and also operating parameter Q, you can get a correlation of the uprising plume velocity, right? And you can find 4.4 is an empirical parameter, and it basically calculated based on cold model experiment. What is a cold model experiment? You must be knowing that you can make a scale down model of the actual prototype. You can make a scale down model into the laboratory, and you can use some low temperature analog for the slag and metal, and then you can simulate the process. And based on some similarity criteria like geometric similarity, dynamic similarity, and the kinematic similarity, all similarity you consider, and then you can choose the analog that way, that is the low temperature analog. Usually the hot metal, there is the hot metal can be, low temperature analog for the hot metal is water, and low temperature analog for the slag is mineral oil. Okay, it has been found that they are dynamically similar. That means the kinematic viscosity is same, both the cases for these analogs. So as a result, we can safely consider there is the hydrodynamic characteristic in the low temperature will be similar to that of hydrodynamic characteristic actually in the industrial scale hot metal. Okay, hot metal slag combination. So that way you can make the cool model simulation, and you can measure the bubble plume velocity, and then you can correlate with the different operating parameters as well as the design parameter, and then you can end up with a empirical constant by regression analysis, like that. So finally you can get this type of correlation, that is the plume velocity, and then average recirculatory velocity, also liquid velocity, can be given as 0.86 of q to the power 1/3 L to the power 1/4 r to the power minus of 0.58. So what does it give? Basically, you can see both the plume velocity as well as liquid velocity, liquid recirculatory velocity, both are directly proportional to the gas flow rate. If you increase the gas flow rate, those will increase. If you increase the height, that will increase. That means a deeper pool will give a better momentum transfer. That is, the deeper pool will give a higher velocity, right? But conversely, that is if you have a wider pool, that is if you have a diameter increases or the radius increases, in that case you can have a lesser velocity both for the flume as well as the liquid velocity. Okay. So this can be estimated actually from this equation, and these are quite reliable correlations. Okay. So this way you can calculate this velocity. Now characterization of the bath mixing. Now whether the bath mixing, how do you characterize whether what is the extent of bath mixing? If you want to quantify that, that is done by the mixing time. Theoretically, mixing time means the time at which the bath will have a uniform composition everywhere. Okay, so if we add some tracer in a moving liquid bath, a tracer somewhere, and then after some time, and if you continuously measure the concentration of the tracer at a certain location or number of location, and then see how it is changing, okay, and then when the concentration at that place will attain the average concentration, then everywhere if it is an average concentration, then that is the mixing time. So thing is that you cannot have a uniform composition exactly. That is, if you just measure, for example, here some experimental facilities has been given, that is you are adding some tracer here and you are nitrogen from the bottom, and then you are monitoring the concentration at the point 1 and 2 at these two location. Okay, you can either 1.1 or 2 or both of them you can take, and then you are measuring the concentration and see when that concentration attains the average concentration. For example, you have added del m amount of tracer and the volume is V, so del m by V is equal to the C bar. So what you want to do, I want to see what is the time required if I just plot the C bar versus time, okay, and then I can have this type of plot will come, okay, like this. This the plot will be like this. So thing is that, and then suppose this is C bar is here. No, that is basically the concentration. That is basically the concentration. It is up. That is the concentration is here, and this is the C bar. This is exactly the C bar. Okay, this concentration is the average concentration, and it is increasing, and then average to pick it up you have to have some time, but you can attain some 95%, right? 0.95 of C. So you can attain the 95% of average concentration at this time, and this is defined as the T mix. This is defined as the T mix. So to attain 90% of the average concentration at any location, okay, what is the time required to attain the 95% of average concentration is called the mixing time. So that is the thing. By noting the tracer concentration at a representative location in the bath, I am calling it representative because you should choose a place where the mixing time is maximum. Because for example, if you measure the value at 2, because there the liquid is likely to be less moving, okay, and because here the liquid strength will be very high here and the movement will be less here. So here the mixing time will be maximum. So if I measure the mixing time at the point 2, that will give you the what situation, that is the maximum mixing time, and you can represent that as the mixing time of the vessel. You can represent that, but whatever you can do, you can take point 1 and 2 and the average of them also you can represent at the mixing time of the vessel. So that's the thing, that by noting the tracer concentration at representative location in the bath, and now representative location may be one location or a number of location, and average value you can represent in the bath, and noting down the time when the concentration attained the 95% of the average concentration, because 100%, if you want to attain the 100%, that is the average concentration, it may take too much of time because of mass transfer limitation. But if you attain 95% of the average concentration, it is declared at the mixing time. Okay, so this is one of the criteria. So this thing I will come it just now. Okay. So this is the thing what I just say exactly, basically the degree of mixing. Okay, degree of mixing basically there is a C by C bar, basically you can say C by C bar. So when C by C bar is equal to 1, that means it is you have just attained the 100%, that is the average concentration. So here you can see, here it is the 90% of this is, you can say 0.9 or something, 95%, right? This is the value is 0.95. This is the 95% point. So this is the time. This is a 40 second. After 40 second, okay, this is 40 basically. After 40 second, this value is, you may not see it, this is the 40. So at 40 second, you roughly attain the 95% of the average concentration, or the degree of mixing is 95%. So degree of mixing, basically we are defining C by C bar, okay, dimensionless concentration. So when it is 0.95, you are defining as as the mixing time. Now the mixing time here can be some value, here can be some value, as I said. So you can take some representative location. You can choose a single representative location, or you can choose number of location, and then an average can represent the vessel, or you can choose some point which is the worst point where the mixing time is maximum, for example 2, and then that will be the maximum mixing time. So you can represent that as the mixing time of the vessel. Okay. So this way you can do that. So this is one criteria, that is called the 95% criteria, or you have another criteria also, that is the criterion 2, it is called the mixing intensity criteria. Mixing intensity criteria is nothing but, that is the, you are measuring, instead of the concentration, if you measure the delta C by T, that is the delta C by delta T, that means the rate of change of concentration at a particular location between two consecutive time, T and T plus delta T. Okay. If you take the difference, so rate of change of instantaneous rate of change of concentration at a particular location. So when the concentration at a particular location doesn't change between two successive time, okay, you call it, say, mixing is, when it is delta C by T is less than 1%, then you can say that it is a mixing has taken place. Okay. So this is basically instantaneous rate of change of concentration at a particular location, right? So you can find this is the way instantaneous rate of change at a particular location is changing, and you can find finally it is coming and becoming steady here. So at around 0.01, that means 1%, right? This is the at 1, that is that. So when it is less than 1%, that is the 1%, this is basically 0.1, you can say this is 0.01, right? This is 0.01, okay. At 0.01, you can define it at. Now, so instantaneous rate of change of concentration at a particular location, representative location, or you can take number of location, average of this, you can define as the mixing time. So when the instantaneous rate of change of concentration at a location or a number of location, average you can take, or at a representative location become less than 1%, you call it as mixing time. Okay. So that is the thing. Here the instantaneous rate of change of concentration at different locations are noted, and average instantaneous rate of change of concentration of the bath is calculated. That also you can do. And when such change become less than 1%, mixing time is declared. You call it as mixing time. So this is the way. So basically the mixing time, what does it give? Mixing time gives and basically a measure of extent of mixing into the bath. Okay. So extent of mixing, or how much time does it take. So lower the mixing time, faster is the mixing. That is the kinetics is also fast in that case. So now mixing time correlations. Now you can see this is a correlation, and mixing time correlation T mix with a, this is basically the specific energy input into the bath, specific energy input, okay. Energy input rate, or you can say specific power input into the bath, or you can say specific energy input rate, sigma as the epsilon m dot, okay. So this is watt per kg basically, and this is the time required for perfect mixing, and you can find there is a good correlation between the mixing time and the specific power input into the bath. You can find there is quite good relation, and this data has been taken from 50-ton argon star ladle, 50-ton ACA escape ladle, and 200-ton RH degasser, 65 kg of water model. So water model is there, and these are all the pilot scale, that is the industrial scale reactor, and water model data is also taken. Cross is the water model data, and you can find all the data. Basically, all data follows the rule. That is the Tm is directly proportional to the mixing time. So this is followed basically. Okay, and you have mixing time correlation with the vessel dimension and gas flow rate. In absence of significant slag layer is also available. This is the T-mix. You can correlate with this thing, and this is also established from the cold model simulation. And 25.4 is the empirical parameter, and Q is the volumetric flow rate, L is the your height of the bath, R is the radius. What you can find is that mixing time become low with increase in Q and with increase in height. So deeper bath and the higher flow rate always give the low mixing time. That means the bath is more highly stirred. Okay, extent of stirring is more. That's why mixing time is less. And again, the same wider the bath, the mixing time become high. Okay. So this is the higher flow rate and deeper pool promotes mixing, and overlying another thing is that this correlation, as I said, in absence of significant slag layer. If you have a significant slag layer, thick slag layer, then mixing time become higher. So overlaying slag layer slows down the mixing. Now specific starting power input in terms of operating parameter, if you just want to calculate that, you can see this is the energy input. Okay, that is the energy input is V into dP, and you can integrate from top to bottom, write that. So V you can write in terms of nRT by P. So then epsilon you can write nRT by T, top to bottom, that is the bottom to top, and dP by dt. And you can write it as epsilon is equal to nRT T bottom minus top, and then that is it is nRT ln of top bottom pressure basically top pressure plus rho gh, basically this is the ferrostatic head rho gh, and then you can write like this. And now you convert to this is the specific rate of energy input. Then what happens, I will just replace, that is the n is basically your what, n is n by, here it will be 22.4, that basically here it is there. I have used it later on, basically here 22.4. So Q is in basically normal meter cube. There is the flow rate. Q is basically the Q dot is equal to the flow rate, normal meter cube per second, say. This is the normal meter cube per second. That is the gas flow rate. So gas flow rate divided by 22.4, this is the rate of moles of gas that is coming in, that is the N. I have made it rate because here also I want to write this epsilon become equal to the rate, that is it is the power input now. So per unit time how much moles of gas is entering, right? So that is the thing. And then R into T, whatever is there. So it is there always. So you can write it 22.4. Right. And then you can write Q by, actually if you write it in moles, then it should be also divided into 10 to the minus 3 also, right? Because it is liter, if you convert it to the 10 to the minus 3, then it becomes your 10 to the minus 3, then it becomes also liter. Because 22.4 liter or 22.4 into 10 to the minus 3 normal meter cube, because that is the thing. So then there is the Q dot by this thing, and RT, there is R is equal to basically the joules per mole degree Kelvin 8.314 T, and then also you convert this, rho density is 7000 kg per meter cube, G is equal to 9.8 meter per second, and H is in meter, then it will be in Pascal, and PT is basically 1 atmospheric pressure in Pascal. If you write it is 10 to the minus 5, so everything in MKS unit, and then you can convert it to this correlation. So the starting specific starting power or the rate of energy input per unit mass can be given by 371 Q dot T ln of 1 plus 0.68 of H. Okay. So this way you can calculate. So simply the specific starting power input in terms of operating parameter you can get. Operating parameter means volumetric flow rate of the gas, temperature, and the height. Okay. So now the effect of nozzle configuration on the mixing. This is very important. We can see we can have a nozzle, except this is basically centric nozzle. You can have very perfectly centered, at the center it is there. Or you can have an eccentric nozzle that is away from the axis, this is this way. Or you can have a slight plug, that is the side plug, just adjacent to the wall you can have a plug. So you can have different kinds of plug. You have a centric plug, you can have at the middle of the side wall as well as the axis, or you can have just at the wall. So now you can see what are the different flow pattern. So what you can find in this case, when there is a centric purging, you have a very strong loop. In the upper loop are very strong, and there are two bottom loop which are weak. Dotted line basically represented weak loop. So this is weak and this is strong, this is strong, this is weak. So this is the flow pattern. So in case of the centric purging, if you have one middle plug means here this thing eccentric purging. Okay, eccentric purging you have, then in that case you have a two loop basically. One is a big loop and that is comparatively mild loop is there, little weak, but it is a big. So big loop is there. Another is a small loop here adjacent to the wall, right? Okay. And in case of the one wall side plug, in this case, third case only one big loop is there. You can find only one big loop in this side. And if you have three middle plugs, for example, you have here, and here. If you have three plugs, then you have this type of flow pattern. Okay. Now let us see the dead zone. If you consider dead zone, in case of the central plug, in this case, you have this type of flow pattern and you have this type of dead zone. Dead zone is there just at the central location, right? Here. This is the basically plan view. Okay. Plan view on the surface. This is on the surface. Plan view on the surface. You have almost, it is very start. And plan view on the bottom, what you can find? Plan view on the bottom, along the wall, you have a dead zone. This is a strong dead zone is there. You can find but the bottom there is a significant area is in dead zone. In case of the middle plug, you can find in the top plan view, you can have only dead zone here because the loop is here from here and then the flow become feeble near this wall because of wall effect. So here you can find one dead zone, that is from the top you can find one dead zone. Similarly at the bottom, although similar location you have a dead zone. Just in this location here you have a dead zone and here also you have a dead zone, that is the thing. Okay, very small dead zone is there. But unlike in the centric purging, there is a big dead zone as well as there are weak loops also. Here is very weak loop. So that's why the dead zone is creating at the bottom, because this is a weak loop. And in case of one side wall, you can have big loop. Here you can find that the bottom, there is the two dead zones are there, and then here it is only one dead zone. And in case of three middle plugs, situation is not good. So what is best configuration out of which is this one, because here the dead zone is minimum. The dead zone is minimum, but otherwise, since there is a weak loop is there, so in the bottom portion, it is not only the bottom layer, and the above up to this 50% half, 50%, you will have a dead zone near this is concentric. This is dead zone is there up to a certain height from the bottom. This will be there because of weak loop at the bottom side. So in case of the one center plug, first thing is that your energy distribution is not uniform, where the top part is circulated very strong, bottom part is not at all circulated strong. There is a very weak loop. As a result, in the bottom section, you have a dead zone like this for a considerable height. So huge dead zone is there in case of the centric plug. In case of the one middle plug, the situation is best. You can find there is only one loop and of uniform energy. Maybe it little mild, but it is complete one loop is there. So, and of the same energy. Okay, so basically the kinetic energy distribution will be much more uniform. So you can have a flow which is of equal strain throughout the bath. And as a result, you don't have any, and there is no location where the velocity, where the momentum transfer is very weak. Only small dead zone is there. Dead zone basically means where the momentum of the liquid is very low or the velocity is very, very low, such that the movement of the liquid may be very negligible compared to the movement of the liquid in the other parts. Okay, that is called the dead zone. That is the movement of liquid is considerably low. That is called the dead zone. And in this dead zone, heat and mass transfer is very weak. But you can find in case of the one middle plug, the dead zone is limited to a very small area as a better configuration. And also the flow is uniform. Flow is uniform. Only one loop is there, maybe little mild, but the distribution of energy is uniform. Okay, that is this thing. And one that is the wall side plug also, you can find the dead zone is maybe better than the centric plug, but also it is not as good as the one middle plug. So, and why, if the one middle plug giving the less dead zone, why should I go for the one side wall plug? Okay, so then in case of the side wall plug also, the intensity of mixing, that is the, it will be also less compared to this, this is there. Okay, so that's why the eccentric purging, this is the second configuration. This configuration is widely used into the industry. One eccentric purging that gives a less dead zone and more uniform energy distribution, kinetic energy distribution. So we have some data here, how uniform the mixing. We have just some data that is here. Basically, we have eccentric purging case we are comparing. Okay, and these are the contour of kinetic energy contour are there, and we are comparing with a reference that is called the induction furnace stirring, because induction furnace is highly uniform stirring kind of. So we have taken this as a reference, and with the reference we are comparing the eccentric purging. So if you can see, in case of the induction stirring, your kinetic energy distribution is more uniform compared to the that is the one centric gas stirred ladle. You can find high energy contours are limited in the top part, 170, 115 and 71 here. Okay. Then below there is 35, then 38, 10, 5. So in this region you can find the kinetic energy distribution is very weak. That is, the kinetic energy is very low. That's why this part is weak loop is there, and very strong loop is there in limited to a very small area in the upper part. So centric purging is not good, and compared to this thing, that is the induction stirring, it is more uniform, right? Okay. So what are the conclusion? That is, the bath homogenization is essential operation in secondary steel making to eliminate the thermal and chemical stratification before casting. And gas stirring is usually adopted in the industry for bath mixing. It is the gas stirring that is used mostly. And bath mixing is characterized by the mixing time. And mixing time is usually measured based on 95% criterion at a local point representing the overall composition of the bath. Especially, most of the cases, there is the single point measurement and the worst point, and then you measure the based on the 95% mixing criteria. That is how much time it takes to attain the 95% of the average concentration. Okay, so that gives the mixing time, and this mixing time basically represents the extent of mixing in the bath. And mixing time is correlated with the specific stirring power of the bath. Okay, so it is usually, and also the mixing time is correlated also bath dimension as well as your operating parameter like gas flow rate. So this is all. That is, the gas stirring is used basically to eliminate the thermal and chemical stratification into the bath, and that is very essential if you want to cast in a modern continuous caster, because continuous caster cannot accept any kind of stratification because it casts liquid with a certain superheat. Okay. Thank you very much.